Welcome to the More You Know Show. Today's lesson is in nuclear chemistry with a focus on fission. With the help of my friends, Emily, Shadia, Peter, and Carolyn, you'll all become experts on this topic. Let's start with the basics. Fission is the process of splitting apart an atom. Usually, uranium-235 is used in this fission process.
Today, the role of the uranium-235 isotope will be played by Peter, Emily, and Carolyn.
An isotope is an element with the same number of protons, but a different number of neutrons, and therefore a different atomic mass than the original element. The number 235 in uranium-235 represents the number of protons and neutrons in the isotope. In the uranium-235 isotope, there are 92 protons and 143 neutrons. What happens in the fission process is a neutron is shot at the uranium-235 isotope, and the striking neutron is absorbed by the atom itself, making the combined number of neutrons and protons 236.
Well, that's all fine and dandy, except this new isotope is relatively unstable, so it begins to fission or split into up to 20 different products. The following reaction is the example of the fission of uranium. Uranium-235 plus 1 neutron yields 2 neutrons plus krypton-92 plus barium-142 plus energy. This reaction is exothermic, which means that energy is released during the course of the reaction. Why mass is lost goes into the good old equation of E equals mc squared. I'll just leave it to my friend Einstein to explain the rest.
Hey guys, my pal Emily was indeed correct when she stated that energy is released. But where in the world does this energy come from? Well, during a typical nuclear reaction, a tiny amount of mass is lost and is converted into energy as a product. This is known as mass defect, which means lost mass that is liberated as energy.
Remember when I came up with my genius equation of E equals mc squared?
This equation explains that energy of a body is equal to its mass times a conversion factor, represented by the speed of light squared. This equation represents the mass-energy equivalence, which states that the mass of a body is proportional to its energy content.
Looking at the equation, it's easy to see that a small amount of mass can be converted into a huge amount of energy because the speed of light is pretty immense, about 300 million meters per second.
Thinking over. Anyway, the energy released in the nuclear reaction is usually released as gamma rays, which are the most highly penetrating form of electromagnetic radiation, and as kinetic energy of the fragments formed. Compared to other chemical reactions, nuclear reactions release a much larger amount of energy. The fission of 1 gram of uranium releases 80 million kilojoules of energy. This amount of energy is equivalent to that obtained by burning 3 tons of coal, or about 600 gallons of fuel oil.
Recall the equation previously shown. Notice that there are 2 neutrons in the product side of the equation, but only 1 neutron in the reactant side of the equation. This is because when a uranium atom is split apart by colliding neutrons, 2 or 3 neutrons are released. These new neutrons can be used to split apart more uranium atoms until all of the uranium is exhausted. Now all of the neutrons released in a fission reaction end up causing another round of fission. If the mass of uranium is small, some neutrons can escape. In order for this chain reaction to occur, we must have a critical amount of uranium, which is the amount needed to sustain a nuclear reaction. Just a little fun fact to know, remember when Carolyn said the fissioning of 1 gram of uranium releases the energy equivalent of 3 tons of coal and 600 gallons of fuel oil? Well, the atomic bomb Little Boy, which was dropped on Hiroshima, contains 64 kilograms of uranium.
That's the energy equivalent of 192,000 tons of coal, which can be used to power a light bulb for 1,300,000 years. Thanks for watching The More You Know Show.
The more you know, the better it is.